So hi there. So you may have been wondering with vectors about why we don't multiply vectors, and we actually do, but it's not an obvious way about how to handle multiplying vectors. And there actually ends up being two different kinds of products that we can actually compute or work with. All right, but they do very different things, and these alternate names will help you. So the first one is called the dot product. All right, and it just has to do with some notation. We put a big dot to indicate that we're using the dot product, but I'll show you that in a minute. And people also call this the scalar product, and that kind of gives you a hint at what's going to go on. Remember, scalars are just numbers. So what's going to happen is we're going to start with two vectors, and we're going to do this dot product on them, and the answer will be a scalar though. Okay, now I want to kind of show you a big advantage of this, and it starts showing a big mathematical advantage to using vectors is that they can shorten a lot of calculations for us. Even if the problem doesn't start out as vectors, a lot of times we can take advantage of vector tools like the dot product to make doing a problem much simpler. Okay, so let me take myself out of this and let me show you an example of what can go on. All right, so okay, so let's look at this problem right here. And so we have this triangle. And see, make sure you realize all we know are the coordinates here. Like this point right here. This point right here is the point 1, 2. This point right here is the point 1, 2, 5, 1, etc. So all I know is those coordinates. 1, 2, 5, 1. And 1, 2, 3, 4, 5. The y coordinate is 5. I don't know why I counted that first. And the x coordinate is 3. Okay, but say I told you to find the angles in that triangle. Okay, you can do it. It's not an impossible task. What you can do is you can use the distance formula to find the three distances on that triangle. Okay, and so you would have these three distances now from the distance formula. Okay, once you have those three distances, let me give them names. And so D1, D2, and D3, and you may have done them in different orders. Okay, but the key thing is, once you have those distances, then you have a side-side-side triangle. And so you could use the law of cosines to find the angles in that triangle. All right, and it's perfectly legitimate to do things that way, but it can be a little bit long of a process. All right, and it's easy to make mistakes. The other thing too is imagine the problem would go the same way, but imagine having a triangle that's drawn in space. So now you have this triangle with three-dimensional coordinates, and you want to know the angles of that triangle. You would do the exact same thing. You would use the three-dimensional distance formula to get these lengths again, and then realize that you have a side-side-side triangle, and so you would use the law of cosines to find the angles. Okay, what we're going to see, and this is what's so nice, is what we're going to see is, notice that process, because of that law of cosines part, there's going to be quite a bit of trig in there. What we can see is we can use the dot product and a couple quick calculations basically to circumvent all of that trigonometry. There will be a little bit of trigonometry in it, but it's actually pretty basic, and just requires a quick calculation and then inverting a cosine. So we'll see this. Let's define the dot product so you can start seeing what I'm getting at. Now, before we define the dot product, what we need to do is define what's called the angle between two vectors. And it's pretty straightforward. Just imagine if I have two vectors here. Say I have the vector u here. And now I could have the vector v started out up here like that. But the idea is that I want to draw them so that they have the common tail. So I'd want to draw v like this, just like whenever we were adding vectors. Okay, so make sure you realize there, this seems obvious, and it is pretty obvious, but there's actually two angles that are formed here. There's this angle right here, but there's this angle, this angle that wraps around that way. Okay, so just whenever we define the angle of two vectors, we're talking about the smaller of those two angles. So we'll use that angle there. Okay, and so make sure you realize that automatically implies that theta's between 0 and 180 degrees. Okay, like that. And make sure you realize we could be talking in radians. So we could be between 0 and pi. Now, when would the angle be 0? That's whenever the two vectors are parallel in the same direction. So we get 180, sorry, we get 0 whenever we have a vector pointing in one direction, and then either a larger or smaller vector pointing in the same direction. And then we'll get 180 whenever 180 degrees whenever they're in opposite directions. Okay, so and then the other situations pertain to the angles in between. All right, now we can find the dot product. Okay, so we're ready to find the dot product. One thing about vectors, and this happened with addition and subtraction as well, is you always want to define, vectors can be done without coordinates. They might be a little bit more complicated, but we can always do vectors without coordinates, so we need a definition that doesn't rely on coordinates. Okay, and so this definition might look a little bit strange to you at first, all right, but it's a coordinate-free definition, and then we'll translate that into coordinates. All right, but given two vectors u and v, what we call the dot product of u and v. Now we do this looks like our regular multiplication sign, and I actually didn't draw that very well. We usually draw a slightly bigger dot than we usually draw whenever we write the multiplication dot, okay, to indicate that it's a dot product. All right, one important thing about the dot product is that it's a scalar. Okay, so I'm going to start with two vectors, but I'm going to end up with just a number over here, a scalar. Okay, and what the dot product is I multiply the two lengths like that, and then I multiply by the cosine of theta, where theta is the angle between u and v. All right, and that doesn't seem like a very good a very useful thing at first, but it's actually a very powerful tool, especially once we get to using coordinates. Okay, but that's the starting picture right there. Okay, so the idea here is that, if say u is right here and v is right here, like that, and then I find the angle between those two vectors, all right, then what the dot product is, I find the length of this vector, or it's given to me, I find the length of this vector, I multiply those two things, and then I multiply by the cosine of theta. All right, and so here's the weird thing about the dot product. It's a very powerful tool, and I'll show you in a minute, and hopefully you'll see. And like I say, that original triangle problem becomes quite easy once we do that, once we have the dot product. But it's a strange thing about the dot product. There's not, I can't draw a diagram here with either parallelograms or triangles or something, and then be able to say, this is the dot product. It's not something physical that shows up in this diagram, but what it ends up being is it ends up being a powerful tool, basically, that allows us to shortcut some trigonometry and a lot of calculations. Okay, so now if u and v are in coordinates, here's where it starts to get. Now I'm going to write this in 3 dimensions. Okay, so but this works just the same in 2 dimensions. Okay, so u would have 3 components in 3 dimensions. V would have 3 components if I'm in 3 dimensions. Oops, that'd be V2 and V3, like that. Okay, then that's actually computing u dot v is a lot simpler if you have coordinates, because what I do, one thing I forgot to mention here too, remember this is a scalar. How is this thing a scalar? Because the length of u is a scalar, the length of v is a scalar, and the cosine of theta is just some number. It's a scalar as well. So you're just multiplying 3 scalars right here, and you're getting a scalar. Okay, same thing here. We need to make sure this gives us a scalar, but what I do is I multiply corresponding coordinates together. So I do u1 times v1, and then u2 times v2, and then u3 times v3. Now that's only if you have 3 coordinates. If you just have 2 coordinates, this part won't be here. All right, and so you'll just have these 2. Now here's the key thing. This answer is supposed to be a scalar, so a very common mistake for students to make is to do those 3 products and then make it into a vector. But this is not a vector product, it's a scalar product. And so what we end up doing is we end up adding those 3 quantities together, and then that gives us a scalar. Okay, and so some people define the dot product this way. I just like to be able to define things without coordinates first, and then put coordinates in there. Now this is an amazing thing too, by the way. Basically, to justify the formula I just wrote, you got to show that that leads to this. So imagine that you start off, you put some coordinates in your picture here. So I'm gonna have to use white to overlay them there. So you put some coordinates in your picture, get the coordinates of this vector and the coordinates of that vector. You got to find the angle theta, okay, using some trigonometry, and then compute this quantity right here, and you can show algebraically that it simplifies down to this simple thing. It's an amazing thing to me. It's like the adding formula to me, that complicated geometry actually simplifies down just to this nice formula right here. Now, one thing too, keep this formula in mind, at least have it on a note sheet, have both formulas. Every once in a while, we do compute the dot product using this formula, okay? Just because in a lot of problems, these three pieces of information are given to us. The coordinates aren't given to us. But I will tell you, especially whenever we're in 3 dimensions, typically we do have coordinates. And so this is the way we compute the dot product. And that's the reason we end up getting a powerful tool. Okay, so say I'm given u and v in coordinates. So I might have u is equal to, this is going to be 3 specific numbers, okay, like that. And then v has coordinates too. And again, this doesn't have to be in 3 dimensions. I'm just writing it in the most general form, okay, like that. And say, so I just have these 3 numbers, so I might be able to draw those like that, okay, but I'm trying to find this angle. Okay, now if you remember the difference, so say here is u and here is v. Remember the main way to get that angle is to be able to use the side triangle and get the angle between them. So what you would have to do, if you remember, u minus v connects the 2 endpoints right there. So right there is u minus v, like that. So then you could get those 3 lengths, and then you would have your side to be able to solve for that angle theta, doing it just completely nuts and bolts. But let's look at that that dot product formula again. All right, that we know that now we know that u dot v is equal to the length of u times the length of v times the cosine of theta. So what could we do? We could solve for the cosine of theta by dividing by the lengths. So we get the cosine of theta is equal to u dot v over the product of the lengths, like that. Now, one finer point too, you got to be in, if I asked you to how you would find the angle theta, you'd probably say to take the inverse cosine. You got to be really careful about taking inverse trig functions because of their domains and their ranges. They could be limited, but this is one place where we get lucky. If you remember, theta is between 0 and 180 degrees, right? Well, how we get lucky is that this is also the range in degrees of the inverse cosine function, like that. And so we get lucky. This is one case where we can actually say this directly. Theta is actually equal to the inverse cosine of that expression right there. And so this is a very powerful formula. So let me show you how we can take advantage of that. Okay, so first let's just make sure we have down A, how to do a dot product from coordinates, and B, how to get the angle between them. All right, and so the idea here is problem 1 will have 2-dimensional vectors and problem 2 will have 3-dimensional vectors. So if you want, you can try to get an idea about what we're going to be looking at here in a moment. So, all right, so we have 1, 2, and then, so we have the vector 1, 2, and then we have the vector 5, 1. So we have those 2 vectors, and so here's the angle that we're trying to find. All right, so the idea here is that the angle between these is the inverse cosine of u dot v over the product of their lengths. So we just need the dot product and each one of their lengths. Okay, so to do u dot v, we just take corresponding coordinates and multiply them together. So we multiply the x coordinates, we multiply the y coordinates, and then we add everything together. So we get 7. All right, and then we need the length of u. The length of u is going to be the square root of 1 squared plus 2 squared, so it's the square root of 5. And the length of v is the square root of 5 squared plus 1 squared, so that's going to be the square root of 26. Okay, and so now we just fill things in. We get theta is equal to the inverse cosine of 7 divided by the square root of 5 times the square root of 26. And so we would just plug that in on our calculators. I'm in degree mode. You could answer in radians if you wanted to. And, you know, some people will tell you specifically. Now, it's one thing very important before you type this in on your calculators. Can y'all see where students might go astray here? Is since I'm multiplying in that denominator, I need to put both of those square roots in parentheses. One other thing you can do too is you can combine those two radicals by multiplying. And so 26 times 5. And then that way you don't have to worry about doing what I just said. Sorry, started talking and wasn't thinking clearly. That's 130. So I could just divide by the square root of 130. That might be a little bit easier to do there. Okay, so I'm going to type in the inverse cosine of 7 divided by the square root of 130. Close my two parentheses, and I get about 52.13 degrees if we were rounding to 2 decimal places. Just remember, we could just as easily convert that to DMS if we needed to, or some other format. So it depends on what kind of problem you're talking about. But that's about 52 degrees, 7 minutes, and 30 seconds if you round to the nearest whole number degrees. Okay, so pretty nice there. And so you've taken this fairly tough trigonometry problem here to get this angle. And notice that it's just a quick, straightforward calculation once you get that dot product down. Okay, same thing here. To get the angle between them, I need to know what their dot product is. Okay, one thing I wanted to point out here too, think about how difficult this problem would be without the dot product. Here we're in 3 dimensions, okay, like that. And so we have about 1, 3, and then, so there's the point in the xy plane. Then I need to go down here to -5. So here's this vector pointing way down, like that. All right, and then I have -2, 4. So I'm up here, and then I got to go up 6, like that. And so we have that vector. You can see that, so here's the angle that we're looking for. Let me do that in a different color. Here's the angle that we're looking for, right? You can see that it's probably obtuse, and but to do that one by hand without the dot product would be very difficult. You could do it, but you would need to subtract the two vectors to get that vector right there, and then you would need to get your side lengths and then do the law of cosines. Okay, but look how easy it's going to be now. And that's kind of the point of me pointing all this stuff out to you, is you can see the beauty of the dot product. But anyway, I multiply the x coordinates for the dot product, plus I multiply the y coordinates, and then I multiply the z coordinates, or components if you want to say that. All right, and so we get -2 plus 12 minus 30. And so I see those two negatives. I'm going to do -32 plus 12. Then it's easier to see that that's -20. Okay, now we still need the length. So now we do the length of u. That's going to be the square root of 1 squared plus 3 squared plus -5 squared. I believe that's the square root of 35, right? We have 1 plus 9 is 10 plus 25. Yeah, it's 35. And then we do the length of v. That's going to be the square root of -2 squared plus 4 squared plus 6 squared. So that's 20 plus 36. That's the square root of 56. Okay, you could write that as 4 square root of 13. If we're just trying to get the angle, that's not going to be terribly important. And so I'm going to go ahead and multiply 35 times 56, knowing that I'm going to combine those two square roots. All right, which is 1960. Okay, and so what that's saying here, if I'm getting ahead of you, I'm going to write this more explicitly here. But theta is the inverse cosine of the dot product, so -20, divided by the square root of 35, square root of 56, like that. it could have been advantageous to write that as 2 square root of 14, isn't it? Yeah, 2 square root of 14. The reason is that 2 would have canceled, would have divided that 20 in the numerator in half. It would have been a little simpler. That's up to you. But anyway, remember I can combine those 2 square roots. So that's the square root of 1960. So my angle is the inverse cosine of negative 20, the square root of 1960. And now I go and type that into my calculator. We have negative 20 divided by square root 1960. And I get about 116.86 degrees. Okay, so there's the answer to the second problem right there, at least to 2 decimal places. If I were to ask you for the exact answer, you would want to give this form right here. Okay, now before we move on and talk about some other geometry problems, this starts pointing something out. Sometimes you can often tell at least how the angle is going to behave just based off of the dot product. Okay, and these are 2 good examples. Notice in this first example, my angle was acute. And in my second example, we could see it in the picture, but our calculation verified it. This angle is obtuse. And what's different in these 2 problems? If you notice the dot product in this one, the dot product was positive, okay? Whereas in this one, the dot product is negative, and that's actually an indicator for how the angle will behave. Okay, so like I was just saying, the dot product describes or predicts the angle type. What you can do too, you can use this to catch errors if you have good pictures. Sometimes you might have a situation where the angle's obviously obtuse, but you get a negative dot product, and so that can indicate an error too. But it can tell you beforehand what type of angle you're going to get. So if your dot product is positive, so remember greater than 0 means positive. Okay, but if the dot product is positive, the angle between them is acute. And then if the dot product is negative, so remember that means less than 0, and so this means negative, okay, then that tells you that the angle is obtuse. Okay, now what's left out of here? Okay, that here we're talking about whenever an angle is positive. Here we're talking about when an angle is negative. Well, what's in between? What's between positive and negative? 0. So what do you think will happen if our dot product is 0? Might want to think about that a second. But if you think about that, think about going from negative to positive. So when the dot product is negative, we're obtuse, and then it becomes positive, and it's acute. Well, what type of angle is between obtuse and acute? That means that you have a right angle. Okay, like that. And this ends up being used quite a bit, this third part of the property right here, okay? So what does that mean? It would mean that you'd have some picture like this. They could be in different locations, but we have a right angle there. What do we call things that are at a right angle? That would mean that U and V, we usually say perpendicular, right? And we can still say that sometimes, but there's another word that covers more abstract cases, and people start using it in more advanced math, and this word is going to be orthogonal. And so what we'll usually say is that if the dot product is 0, that tells us that U and V are orthogonal. Okay, so the thing about that, just like with that last example, you could be given U's coordinates, you could be given V's coordinates, and you're asked to find the angle between them. Well, notice that the first step that I did in the last one is I computed, the last 2 examples, is I computed that dot product, okay? And so say that came out to be 0, all right? Do I need to go through and find the lengths and then do that inverse cosine? And then do the inverse cosine? You can, it'll give you the same thing, but you don't need to. If you get that the dot product is 0, then you automatically know that the angle between them is 90 degrees. Now these other 2 properties just tell you what type of angle you're going to get. They don't tell you what the measure is, but definitely if your dot product is 0, your angle's automatically 90 degrees. All right, so let's use the dot product to solve some geometry or trig problems. And so if you remember, I drew it kind of rough hand, but I started to put it in the video, but I didn't like how sloppy the picture looked. So let's go back to that first problem we talked about. Okay, so let's get this in terms of a problem now. So we'll do this as an example. And say I tell you, instead of just finding the angles, let's, trying to make that picture smaller, let's solve the triangle, okay? Okay, so you might remember that from trig class. If you don't, what that means is to find all the side lengths. I'll just call them the sides and the angles. Okay, like that. So let's go ahead and label. Gamma. Some people do use capital letters instead. So if you don't like using the Greek, you can. Now, okay, so we talked about one way using trigonometry and the law of cosines, but let's talk about another way we can do this. Okay, and so let's just start focusing on an angle right here first. And since beta is over on the left, I'm going to start with beta. Okay, now remember we're going to try to use vectors in the dot product to do this. And what I mean by this is find the angle, okay? So we'll want to find the angle between two vectors. The important thing about using that formula, though, is the two vectors need to be drawn so that they have the same tail, all right? So to figure out what beta is using vectors, I would want to draw this vector right here, and I would want to draw this vector right here, okay? And let's give these points names as well. So, let's give them the name, the capital letter. Well, no, let's call it P, Q, and R. Hope that notation's not getting a little out of hand. So P, Q, and R are the points. Okay, like that. And so for beta, what it's going to be is it's going to be the angle between the vector that goes from P to Q and the vector that goes from P to R. Like that. And since these are vectors between 2 points, we'll use that tip minus the tail idea. So to get the components for the vector PQ, I take the coordinates for Q, which would be 3 and 5, and then I subtract off the coordinates of P, which would be 1 and 2. So the vector PQ is in coordinate form or component form is 2, 3. Okay, notice also that that's also going to give me this length A. All I have to do is find the length of that vector. But the reason I started with this angle is I wanted to point out that you have to draw those vectors so that they have the same tail, because that's going to affect how we set things up to find either alpha or gamma. Okay, so anyway, there's PQ, and then PR. It's going to be the coordinates of R, which are 5 and 1. And then I'm going to subtract off the coordinates of P, so 1 and 2. So the coordinates of PR are 4, negative 1. Okay, and notice PR gives, the length of PR gives me C. So I can already get started on those because I'm going to need them in the dot product. So what I'm going to end up doing is up here, I'm going to end up writing my answers. Okay, but let's stick with beta. I started to get a little sidetracked. Okay, so to find beta, it's going to be the inverse cosine. And the reason is those links are going to show up. So remember before I was using U and V, but to find the angle between two vectors, you take their dot product. So it'd be, my vectors now are these vectors, PQ and PR. And then I divide by their individual lengths. All right, like that. All right, so I do the dot product, inverse cosine. If I do the dot product, I multiply the corresponding coordinates. I was thinking of the answer and I got 2 times 4 plus 3 times negative 1, like that. And then I divide by their lengths. The length of PQ is going to be the square root of 4 plus 9. That's going to be the square root of 13. The square root of PR, that's going to be 16 plus 1, which is 17. Okay, now remember too, this is the length of PQ, right? But the length of PQ is also this A right here. So I could start writing some answers. I'm just going to write my answers down at the very bottom here. So what we just figured out is that length A is actually the square root of 13. Okay, what's that square root of 17 giving me? That's the length of PR. That's this length right here. So this is that C that was in my original. Okay, so I'm going to save some room for B. Okay, but then C is the square root of 17. All right, like that. And now we can get beta too. All right, so in terms of our answers here, we'll have alpha and beta and gamma, like that. All right, and so what do we have? We have the inverse cosine of, oh, I didn't finish this, sorry. So we have the inverse cosine of 8 minus 3 is 5, and then divided by the square root of 13 times 17. That's 221. Okay, like that. So now I do the inverse cosine of 5 divided by the square root of 221. That's about 70.34 degrees. Okay, like that. Now you probably want to store that because remember, if I want to, all I really have to do is find two angles. If I've saved them, then I can just subtract from 180 to get the third angle. So I'm going to store that angle. The normal TI-84 graphing calculators won't store Greek letters except for theta. So I'm just going to save it in B since I won't need B and saved for my length. Okay. So anyway, there's beta. Now we got to come back, all right, and we have to find another angle. So the key thing is now, let's find alpha. Okay, so for alpha, again, you need those vectors going to have the same tail. Okay, so this is going to be the angle. Let me draw a line to separate these. This is going to be the angle between, our common tail has to be R. So I got to turn this vector around right here. Okay, I got to, oh geez. I want to undo that. Oh, I can't undo erases. All right, so anyway, sorry about that. So this was R. This had coordinates 5, 1. I think that's all that I erased. So anyway, I need to turn this vector around so that they have the same tail. So I'm going to have this vector right here, and then I'm going to have this vector right here. So in terms of writing our vectors in terms of letter notation, what's the angle is going to be between what two vectors? It's going to be the angle between RP and RQ. Okay, like that. And so we need to get those coordinates. Sorry, I'm writing in a different color. Okay, now for RP though, it's easy. We don't have to go through the whole process because a moment ago we did P to R. All right, and so all you're going to be doing is reversing the subtractions. So that's just going to make these signs change. All right, so R to P is going to be -4, comma, +1. Okay, now when you have to do R to Q, all right, so we do the coordinates of the tip, which would be 3 and 5. And then we'll want to subtract off the coordinates of the tail, which would be 5 and 1. Like that. So R to Q is the vector -2, comma, 4. All right, so we just carry on now. And so the angle alpha is going to be the inverse cosine of the dot product of those two vectors, RP dot RQ divided by their lengths. Oops. Like that. Okay. So RP dotted, so we have the inverse cosine of RP dotted with RQ. That's going to be -4 times -2 plus 1 times +4. And then divided by the length of RP is going to be 16 plus 1, so the square root of 17. I should have already known that because we found C before. And then we do the square root of square each one of these components and add them together. So we got 4 plus 16, which is the square root of 20. Okay, like that. And so my numerator, the dot product part, then becomes positive 8 plus 4. That's going to be 12. And then 17 times 20 is going to be 340, I believe. Let me double check though so I don't mess this up. Yeah, then divided by the square root of 340. Okay, and so I can type that in, and so I get the inverse cosine of 12 divided by the square root of 340. That gives me about 49.40 degrees, and that was alpha. Okay, like that. Notice also that we got B in our calculation. I don't know if you realized, but here's B. That's the length of this vector R to Q. And so that would be this. So that's the square root of 20. You probably want to simplify that too if you're given it as an answer. So B is 2 times the square root of 5. So gamma is the only thing that's left, and then we'll be done. And notice that as long as you have alpha still on your answer line, or you could store it if you want to, especially if you think you might need it later. Okay, so yeah, let's store that to the letter A. So I just hit stow or store, and then I told it to store it to the letter A. So now to get gamma, remember the angles in a triangle have to add to 180 degrees. So gamma is just going to be 180 minus alpha minus beta. And just remember I saved alpha and beta to the letters A and B. So we get 180 minus A minus B. And that's about 60.26 degrees. Like that, okay? And so there is the solution to that triangle. All right. One other thing too you could do is if I asked you for the area of the triangle, okay, I don't have room to write this, but if I asked you for the area of that triangle, remember that if you have a SAS triangle, so if you know two sides, I'm just going to call them A and C since they're in that picture right there, and if you know the angle between them, like that, then the area is 1/2 product of the sides times the sine of the angle between them. So all I would have to do, I don't have room to go through that all, but I could take A times C times the sine of B. I can calculate it real quick because I have that. So I have 1/2 times the square root of 13 times the square root of 17. I forgot to close a parenthesis though. I'm going to go back, put that parenthesis in there. Be careful with your parentheses. And then times the sine of beta, I have that saved as B. Like that. Wow, that's amazing. Did you try that to see why I'm saying that's amazing? The area of that triangle right there is a perfect number, 7 square units. Okay, and so once you have the triangle solved, there's all kinds of things. Make sure you realize you could also get the perimeter easily just by adding A, B, and C. So those vectors, I know this all looks pretty complicated, and maybe I was moving a little bit fast, but it's just a real fast, easy calculation, and you don't have to focus so much on the law of cosines and stuff. So this is shortcutting that whole law of cosines calculation. And you can kind of see the law of cosines embedded in there. If you remember using the law of cosines to find an angle, you're adding things in the numerator and then you're dividing by two lengths. So you can kind of really see the law of cosines in there if you look at it carefully. And then I'm also going to mention an app in physics that's called Work. Okay, now this is actually a physical kind of quantity. And what it is, it's a measure of the energy required to move an object. Okay, so say you have a box on the floor, just to illustrate this, okay, and say you're going to push it to move it, okay, like that. Now I'm pushing it, okay. So think about it. If I push straight on that box, it's going to require less energy to move that box along the floor, okay. But say for some reason maybe you're a really tall person, and so you're up here, and so whenever you push on that box right there, you're kind of pushing down on it at an angle. So part of the energy in moving that box gets pushed down into the floor, and part of it gets moved horizontally. So that's going to require more energy to move that box. And so that's what work tries to do, is it's kind of a measure of how much energy is required to move an object. Okay, like that. Now, whenever I'm pushing on that box, I'm exerting a force. Okay, and so we'll call that F, and so that's the force used to move the object. Okay, like that. And then notice that this object starts in one place and moves to another place. So that's actually a vector. It's a displacement vector, and so we call that D, like that. All right, and here's the nice thing. So D is the displacement of the movement, like that. Okay, and then there's just this nice formula that the work is equal to the dot product of that force vector with the displacement vector, like that. So it's really nice. Now the units for force, or for work, I'm sorry, we got to think about what system we're in. Okay, so in the English system, you can, in terms of analyzing the units, you can think about this as just being a regular product of numbers. So this is a force in the English unit. The standard unit is pounds. Okay, like that. And then the standard unit of length in the English system is feet. So the units are pounds times feet, and people will usually pronounce those as foot pounds. Okay. One thing to understand about that, no matter which system you're in, these are actually energy units. Okay. And then it'll help you with the metric system. In the metric system, the standard unit of force is the Newton, and the standard unit of length is the meter. So some people answer work problems as these are called Newton meters. Okay. But that's equivalent to another unit called a joule. And so some people will answer those in joules. Okay, so I'm going to leave that there for now. For me, I'm mostly concentrate on the mathematics part of it. So I'm more interested in you getting down the geometric ideas of the dot product and how we can use it. And the main thing about the dot product, it doesn't show up in a picture. You can't draw a picture and say, there's the dot product right there. But it's just that powerful tool of being able to find angles, either between vectors, or if you're willing to use vectors from points, you can start a problem that has nothing to do with vectors. See, that triangle problem had nothing to do with vectors. But if you're willing to convert things into vectors, you can take advantage of that vector formula with the dot product to make doing all that trigonometry a lot simpler. You can see it's still complicated, so I'm not saying it makes your life completely simpler, but it does help a lot. So I hope that helps, and I wish you the best, and let me know if you have any questions.